Hello guys, welcome back to another video on my channel. So in the last video we did a nice integral by Ramanujan. In this video I want to, dwell more into the idea of special functions. And we're actually going to consider two special functions that we already have used in the previous couple of videos, namely the elliptic integral functions. And we're going to do identities on them. So let's get started. Okay, so starting off, let's define things. Capital K of K is going to be elliptic integral function of the first kind, which is integral from 0 to pi over 2 d theta divided by square root 1 minus k squared sine squared theta. Now, with a couple of substitutions, you can rewrite this as 1 half integral 0 to 1 dt over square root t times 1 minus t times 1 minus k squared t, and this is the form we're going to use for this video. Similarly, we have the elliptic integral function of the second kind, e of k, which is usually defined as integral from 0 to pi over 2 square root 1 minus k squared sine squared theta d theta. So the same thing but in the numerator, which with a couple of substitutions can be expressed as 1 half integral 0 to 1 minus k squared t divided by square root t times 1 minus t times 1 minus k squared t dt. Okay, let's get started. So we have a capital K prime of K, where differentiating 1 with respect to K is 1 half integral 0 to 1 of, and we're gonna have to use the chain rule here because we have power 1 half and in the denominator. So we get 1 half integral 0 to 1 kt divided by square root t times 1 minus t times 1 minus k squared t whole cube dt. I'm assuming you're familiar with this kind of calculation using the chain rule. So I will leave that to you to figure out. If you don't agree with me, you can always pause the video and do it on a piece of paper. So that equals 1 half integral 0 to 1. First, let's multiply and divide by k. So that's this k in the denominator. And kt gets another k, so that's k squared t. And then we're adding and subtracting 1. So it's a little involved, this step. We're first multiplying and dividing by k to the original form, and then we're adding and subtracting 1. The rest of it is the same. So we have square root t times 1 minus t times 1 minus k squared t whole cube dt. This we can break into two parts. So we're going to take the k squared t minus 1 as one part and the separate one as the other. So we take that, we have 1 minus k squared t, and since we had k squared t minus 1, we're just going to multiply by a minus. So minus 1 has integral from 0 to 1. 1 minus k squared t dt divided by k times square root t times 1 minus t times 1 minus k squared t the whole cube, plus 1 half integral 0 to 1 dt divided by k times square root t times 1 minus t times 1 minus k squared t whole cube. Now I'm just going to take the k that was in the denominator, I'm going to multiply that, cross multiply that to the left hand side. So we get k times capital K prime of k equals minus 1 half integral 0 to 1 dt. And we noticed one of the factors will cancel out. We have factor of 1 here for the 1 minus k squared t, and we had a factor of 3 by 2. That leaves us with square root t times 1 minus t times 1 minus k squared t plus the second term, which is we can express that differently. So 1 half integral 0 to 1 dt, we can take one of the 1 minus k squared t factor and keep it in the integral, and the squared factor from the cube power we can pull out. So 1 minus k squared t times square root t times 1 minus t times 1 minus k squared t. I'm repeating, so we had power 3 here. So 3 is 2 times 1. So power 2 inside a square root we pulled out as just this factor, and we had the remaining power 1, which is trapped inside the square root still. That's all I've done. Now this first integral is just capital K of k, right? Just by definition, with a minus, of course. And the second integral is, we can just keep it as it is. Now what I'm going to do is, apart from that, I'm also going to multiply it by a factor of 1 minus k squared on all sides. So I have 1 minus k squared times k times capital K prime of k equals minus 1 minus k squared. And as discussed, this is capital K of k plus the same integral, 1 half integral 0 to 1 minus k squared dt divided by 1 minus k squared t square root t times 1 minus t times 1 minus k squared t. So we can just add this this lone k term on the left hand side again. So we get 1 minus k squared times k times capital K prime of k plus 1 minus k squared times capital K of k equals this integral 1 half integral 0 to 1. Now what I'm going to do is, we have the 1 minus k squared term. I'm going to keep that in the middle. I'm going to add the term 1 minus k squared t the whole squared on the left side. And I'm going to subtract the same term, 1 minus k squared t the whole squared, on the right side. The denominator is the same, 1 minus k squared t square root t times 1 minus t times 1 minus k squared t. And I'm going to actually split this again. So we can take the 1 minus k squared t whole squared term in one integral, and the rest of the terms in the second integral. So when I do that, I notice the square cancels out with the power 1 in the denominator, giving us a power 1 in the numerator. So we have 1 half integral 0 to 1 minus k squared t dt divided by t times 1 minus t times 1 minus k squared t plus 1 half integral from 0 to 1. And now if we consider 1 minus k squared minus this entire square, and we expand it and cancel some terms, we're going to end up with k squared times 2t minus 1 minus k squared t squared dt divided by 1 minus k squared t times square root t times 1 minus t times 1 minus k squared t. Now everything is good until this point. Everything was obvious until this point. And here comes the big twist. So first of all, the next obvious thing to do is to notice that this integral, the first integral on the right side in this pink that I'm circling, is actually e of k. So I'm gonna move that to the left side, which gets a minus. So the left side becomes 1 minus k squared times k times capital K prime of k plus 1 minus k squared times capital K of k minus e of k equals the integral 1 half 0 to 1 k squared times 2t minus 1 minus k squared t squared divided by 1 minus k squared t square root t times 1 minus t times 1 minus k squared t. Here's the twist. How do we evaluate this integral? Well, let's take a detour a little bit. Let's consider the derivative with respect to t of the function square root t times 1 minus t divided by 1 minus k squared t. It's all under 1 square root. So when we have to differentiate, we first have to do the quotient rule and the chain rule, basically. So we have square root 1 minus k squared t times t times 1 minus t, the whole thing to the minus 1 half power, 1 half times 1 minus 2t plus square root t times 1 minus t times k squared over 2 times 1 minus k squared t to the minus 1 half divided by 1 minus k squared t. We can simplify this using algebra. Mainly, we can find a common denominator by cross multiplication. So we get 1 half 1 minus k squared t times 1 minus 2t plus k squared t times 1 minus t divided by 1 minus k squared t times square root 1 minus k squared t times square root t times 1 minus t. We can simplify this further. 1 half times 1 minus 2t plus k squared t squared divided by 1 minus k squared t times square root 1 minus k squared t times square root t times 1 minus t. And this is very close to the integrand we have here. It's just that there's a discrepancy of a minus sign and a k squared, of a minus k squared factor basically. So that's all we're going to do. So the left side is the same, 1 minus k squared times k times capital K prime of k plus 1 minus k squared capital K of k minus e of k equals minus integral 0 to 1 of k squared times the derivative with respect to t of the function t times 1 minus t over 1 minus k squared t whole under root integrated with respect to t. And by the fundamental theorem of calculus, this is just minus k squared of the original function inside, which is square root t times 1 minus t over 1 minus k squared t, evaluated at 1 minus evaluated at 0. But it so happens that if you evaluate it at 1, you get 0, and if you evaluate it at 0, you also get 0. So the right hand side is identically 0, and we can just rearrange this entire equation, which equals 0 anyways, to give us d of capital K of k over dk, which is another form of k prime of k, equals e of k minus 1 minus k squared of k divided by k times 1 minus k squared. Now you may notice this is sort of like a coupled differential equation, because we started with k, and we're getting some mixed terms in e. Okay, fair enough. Let's look at e now. Let's see if we get a couple terms like this. So capital E of k equals 1 half integral 0 to 1 1 minus k squared t divided by t times 1 minus t times 1 minus k squared t dt. Let's differentiate E of k with respect to k and multiply by k. So that gives us negative 1 half integral 0 to 1 k squared t divided by t times 1 minus t 1 minus k squared t, and we're adding subtracting 1 because of the way the process goes, and we have a dt there, equals minus 1 half integral 0 to 1 k squared t minus 1 divided by square root t times 1 minus t 1 minus k squared t minus 1 half integral 0 to 1 dt over square root t times 1 minus t times 1 minus k squared t. And with just this, you realize that this integral here is just e of k, and that is k of k, and then we can just divide both sides by the small k. So we understand that e prime of k equals e of k over k minus capital K of k over k. So again, we see there's a mixed equation here, because in the equation for e, in the differential equation for e, we are actually getting k. So it's kind of coupled. How do we uncouple them? There is a way to uncouple them. Let's take another higher derivative. So another derivative with respect to k, and we get d over dk of 1 minus k squared times k times capital K prime of k equals d over dk of e of k minus 1 minus k squared of k, just using the k prime equation that we have, gives us e prime of k minus capital K of k times 1 minus 2k minus 1 minus k squared times capital K prime of k equals e prime of k plus 2k times capital K of k minus e of k over k plus 1 minus k squared over k times capital K of k. So what I've done here is just substituted for k prime of k, because we know what that is. And in the next step, we have k times capital K of k plus e prime of k minus e of k over k plus k of k over k. And when we substitute for e prime of k, e prime of k just cancels off with these other guys, because this entire term apart from the first term is identically 0 because of the equation for e prime of k. So we just end up with the equation 1 here, which is k squared minus 1 times d over dk of k times sorry, that's I meant to say equation 2. So d over dk of 1 minus k squared times k prime of k equals k times capital K of k. That's equation 2. That's really uncoupled because now there's no E dependence. Similarly, we can uncouple the E equation as well. So we can differentiate with respect to k times E prime of k, which gives us d over dk of E of k minus k of k. This becomes k squared minus 1 times d over dk of k times E prime of k. I'm just multiplying both sides by k squared minus 1 equals k squared minus 1 E of k minus capital K of k over k plus, because this first term is just the differential for E of k. This first term is just after substituting for E prime of k. Second term is substituting for k prime of k. So plus E of k minus 1 minus k squared k capital K of k over k. And we can simplify all of this nicely. Many things cancel off, and we get equation number 1, which is k squared minus 1 d over dk of k times capital E prime of k equals k times E of k. That's equation 1. So you see that that's uncoupled too. It's just that it became a second order differential equation because we're differentiating E twice. So this will become an E double prime if you sort of expand expand and apply the derivative using the product rule. Similarly with the k equation as well. This has a sort of nice, suggestive looking, Sturm Liouville kind of form. And since it's the second order differential equation, you might say, what's the second solution? Well, another solution for equation 1 is obtained by doing a slight change of parameters. So E of square root 1 minus k squared minus capital K of square root 1 minus k squared is another solution for 1. And another solution for 2 is capital K of square root 1 minus k squared. So you kind of see this symmetry going on. I mean, in fact, if you set k equals sine theta, square root 1 minus k squared is actually going to be cosine theta. So you see there's a kind of a sine cosine kind of symmetry going on here, which shouldn't surprise you given the original form of these elliptic integral functions. So I think that's it for this video. I apologize if for any mistakes. Let me know what you think about these nice identities and these nice functions. And see you next time. Peace out and goodbye.